Now let's do a numerical example and see how we can utilize the concepts we have learned so far. So let us assume a function y of t. This function is actually unknown to us, sine x1 plus half x2 square, and our goal is to find an approximated function, right? What we know is that we know only the inputs x1 and x2. Okay, so using the inputs x1 and x2, we will be approximating this function. Now let's proceed with the mathematics. So the first neuron, n is equal to 1. The first step is to do the linear combination. So z1 is equal to w11 x1 plus w12 x2, right? Now I know the inputs, but what are the values of these weights? So I need to initialize these weights to some values. So let us assume w11 is equal to 1, w21 is equal to some value. Let's suppose this is equal to 0.5, w12, let's suppose this is equal to -1. It can be any values. Okay, and similarly let us assume the output weights are 1 and -1. Okay, so z1 is equal to 1, x1 is 1, right? I know these values. w12 is equal to -1. What is the value of x2? This is 0.5. So this actually becomes 0.5. Now the next step is for a single neuron, what we need to do is linear combination and then activation. So the next step is activation. So h1 is equal to sigma 1 of z1. Since we are using sigmoid function, so this will be written as 1 divided by 1 plus e power minus z1. Okay, so this becomes 1 divided by 1 plus e power minus 0.5. So the value of h1 is 0.6225. So this is for the first neuron. Okay, now for the next neuron, n is equal to 2. The first step is to do the linear combination. So z2 is equal to w21 times x1 plus w22 times x2. You remember this, right? This x1 needs to be here with the multiplication of w21. Similarly, for this input, which is x2, w22 will be multiplied with the x2, and we will reach this point, which is for the second neuron. So this is the linear combination for the second neuron. So now let's use the values. So w21 I assumed 0.5, x1 is 1, right, plus w22, that is 1, x2 is 0.5. So this becomes 1, right? Now the second step is activation function. So activation, h2 is equal to activation of z2, which is 1 divided by 1 plus e power minus z2, which is equal to 1 divided by 1 plus e power minus 1. So h2 is equal to 0.7311. You can confirm these values using your calculators. Okay, now I have h1 and now h2. So we know that the estimated function y hat of t is equal to v1 h1 plus v2 h2, right? What is the value of v1? This is 1, I assumed here. What is the value of v2? This is -1. So v1 h1 is, we derived this value 0.6225 plus v2, that is -1. So what is h2 here? 0.7311. So this becomes, let me see, what is the value of estimated function? So this becomes minus 0.1086. This is my estimated value, right? Now what we are going to do is we are going to find the real value of y. So let's see what is the real value and input the values of x1 and x2. So this becomes sine of x1 is 1 plus half x2, so 0.5 square, right? So this becomes sine 1 plus half 0.5 square. So we get y of t equal to 0.9665. Please check the values using calculators. So now my estimated value is minus 0.1086, but my real value is y of t is equal to 0.9665. So there is a big difference in this value. It means the neural network is not performing well. Let's find this value. E is equal to y minus y hat. So this is 0.9665 minus 0.1086. So E is equal to 1 point. Let me set this. Yeah, 1 point. No, sorry, I'm unable to choose the pen. Yes, I think it is chosen now. Yes, so E is equal to 1.0751. There is a big error. Now our goal is to minimize this error. So what we are going to do is we are going to use back propagation and gradient descent methods, and using that we will update the values of these weights, W11, W21, all these weights and output weights. Accordingly we will derive some formulas. So using that, once we initialize these values with some values, these values will be updated. So we will have continuous iterations, and this error will gradually reach to 0, and we will have the accurate approximation of y using this neural network.